Hi everyone. Sorry about that. Just a little bit of technical trouble. I think we're ready to get started now. I'm Albert Steppi. This is Matt Haberland. We actually have Pamphil Roy joining us today too. We're maintainers for SciPy, particularly stats, and welcome to our tutorial on intuitive statistics with SciPy. I'm going to be presenting. Matt and Pamphil will be able to help you if anyone has any questions. First of all, show of hands, how many people here have had at least one intro statistics class? Pretty much everyone. How many people just know their stats solid, frequentist stats, hypothesis tests, confidence intervals, and could just use that? And anytime, how many people have a more advanced background in stats? Cool. So all right. So we tried, we're not sure who's going, the level of people show up. I tried to target this so that even people without a stats background could appreciate it, but hopefully it's still going to be interesting to people of all levels. Ideas, kind of give a fresh perspective on frequentist statistics while learning how to use SciPy's tools for Monte Carlo and randomization type tests. And all right, so things we're going to learn about today. First, we're going to build up hypothesis testing from first principles through the lens of computer simulation. And we're going to look at the Monte Carlo test, where you do a hypothesis test basically through simulation. We're going to look at permutation testing, and we're going to look at the bootstrap, which at least when I first learned about it seemed like magic. I don't know how many people know about the bootstrap. It lets you get an idea of kind of the uncertainty in an estimate, sampling from a distribution. Don't worry if you don't know what that means yet. Okay. Oh crap. The pop filter came off. Okay. So, starting out, hypothesis tests and first principles. The very idea, we're just going to start from the very basics, the idea of randomness. Now, imagine flipping a coin. Most people want to say a coin toss is random. There's a probability 0.5 of getting heads. Each is equally likely. What do we mean here by random? Because obviously, if you were to know the exact initial conditions, the velocity and the angle at which a coin was flipped, the weight distribution, the shape, air, pressure, and wind, you could probably predict exactly the outcome of where that coin is going to land. So is this a deterministic process? How is this random? Well, the idea is, given the information that we know when this coin is flipped, there's no way for us to know the outcome, whether it will be heads or tails. Each will be equally likely. So for the idea of statistics here, whether or not randomness is a result of our own incomplete information or due to some inherent uncertainty in the world, like some people believe happens in some interpretations of quantum mechanics, it doesn't matter. We do statistics in the same way. All right, so again, what do we mean by randomness when we flip a coin? Because it's not just the probability heads. If we want to know, it's just given the information we have no way to predict the outcome better than chance. All right, so I guess if we had a fair coin, this is the idea, equally weighted, equally likely to come up heads or tails, we say the probability is 0.5, but a weighted coin might come up heads at a different rate, 0.7, 0.8. And so kind of the idea of frequentist probability comes out of this. It's the idea is if you just keep flipping this thing and you keep track of the proportion of heads you get so far, what is going to be, where is this going to converge to eventually? If the coin is fair, eventually this proportion is going to go to 0.5. And we say this is frequentist probability. If the coin was unfair, eventually, it might go to 0.7. It's biased towards heads or something. So frequentist probability, the idea is that we have some process or event we want to study, and we play it back again and again and again, And in the long run, there's, the probability of the outcome is the proportion of this happening out of all of the trials. So then we come here as like frequentist probability about imagining trials. No, it's about experiment. It's a very practical idea of probability where, you run experiments again and again to try to get a, calculate what like Fisher, one of the originators, is called an objective probability. Now, a lot of people know about Bayesian probability, think maybe this is a more advanced thing. Bayesian probability is actually earlier. Fisher was originally a Bayesian. He wanted to come up with what he called like an objective measure of probability. Now, there's a lot of debate about frequentist versus Bayesian methods. I like to think just in pragmatics, these are tools. Some of them are useful for different purposes. These randomization tests here can be very useful, and frequentist statistics is a good thing to know. All right, so there's this other idea here. I wrote down independence. Is the idea the outcome of one coin toss is not going to impact the outcome of any future tosses. It's not going to impact the outcome of any past tosses either. We say, in this sense, they're independent. This is just the intuitive definition of this. There's actually, we don't need the precise one. So here's our first little experiment here. How well does everyone think they'd be able to generate their own random numbers? Like, can you, just with the power of your mind and free agency, generate a sequence of numbers which are statistically random, meaning that there is no way to predict the outcome based on some analysis of, past results, which would let you predict future outcomes at a rate better than chance. So I want to give everyone a chance to try this here. So there is, I think I had a value filled in there in your notebook. Just go ahead and blank that out. There's 50 X's there. 1 is heads, 0 is tails. Try to, in your mind, simulate a coin toss for 50 flips. I'll give everyone a minute or two to do this and see how random can you be. Anyone still working on their coin tosses? All right, we're good. All right, we're going to use this later for some of our analysis. So now the next question is, can a computer generate random numbers? And I don't mean like some special like coprocessor that like looks at some random phenomena, but a deterministic algorithm. Can it generate random numbers? I mean, can it, strictly speaking, generate random numbers? No, right, I see, because like, it's a deterministic algorithm. Like, if you know the algorithm, you can with 100% certainty predict what's going to happen next. But there's a curious fact in math that a lot of deterministic processes appear random. I don't know how many people are aware of the Collatz conjecture in mathematics, but I'm not going to go into it. You have this deterministic sequence. It's probably like the hardest problem anyone's ever thought of because like there's no results on it whatsoever. But you have a process. It's completely deterministic. The theorem is basically prove that it behaves as if it were random. No one can do it. But there's a lot of just deterministic algorithms that appear random. And here is a very simple one from the early days of Monte Carlo, which Monte Carlo simulations came out of the Manhattan Project, actually, to like calculate yields of nuclear reactions and things. John von Neumann and Stanislaw Ulam were the originators of this. Well, here is this algorithm here. The linear congruential generator is one way a computer can generate random numbers, and it's very simple. You have some initial value, your seed, you have constants, A, C, and a modulus. You take your seed, you multiply it by a constant, you add another constant, and then you take the remainder by the modulus, and you repeat this process. Now, this can't be random. It's deterministic, but for the most part, this is good enough. We see here. Here it is. I wrote a simple class that we can use this. You can, these are parameters it takes, the constants, a seed, a modulus. All right, you can generate a random integer by taking the next, iterating to the next step here. Here we are mapping this. This is, see this default modulus is 2 to the 32. So then by here we're mapping, there's like 2 to the 32 possibilities here. Here we're mapping this to a uniformly in the range of 0 to 1. So we're doing a linear scaling from like generating random integers from between 0 and 2 to the 32nd power minus 1. Map that to 0, 1. And here we have our simulated coin toss at the end here, where it's heads if this random number between 0 and 1 is greater than 0.5. Otherwise, it's tails. All right, so I'm going to instantiate this with the seemingly everyone's favorite seed for an example. And wait, oh, I didn't do my imports. Why did I not do that? Oh, because I never even ran this cell. All right. But here we are. We're generating some random numbers. I just 10 numbers between 0 and 1. And here, make a histogram of these. Seems pretty random. For only 1,000 can do a couple more. All right, so through histograms, I think most of you know what a probability distribution is, but given a bunch of possible outcomes, if this is discrete, each of them gets a probability. They add to 1. If this was a continuous distribution, then your possible outcomes are real numbers on some scale, in this case between 0 and 1. And a distribution function like this would give you, you could imagine, it's like you take the limit as the number of bins gets smaller, and then you get a function where the area between 2 points tells you the probability that the variable like the outcome lies between those two. All right, so now we're going to do a little code along, and we're going to work out a hypothesis test to test if a coin or your imaginary coins are fair. Are they biased or not? So the idea here basically, if a coin is fair, we should expect it to come up heads as roughly as often as it comes up tails. So the idea is, all right, let's flip this coin a bunch of times, calculate the number of heads. And the actual number is up to chance, but I mean, the idea is if it's really far away from the expected 25 here, if we do it 50 flips, then, that seems pretty unlikely. Whereas if it's close, that's pretty reasonable to have happen. So how do we make this into a formal process, though? It's probably not a good idea just to eyeball it and be like, all right, I got 30 heads. That's not too far off. I think this coin might be fair. So the idea here is a decision rule for hypothesis tests. I wrote 20 here. Maybe this should be, where is that? Oh. All right, lost it. All right, but we're flipping a coin. All right. 50 times. Counting the heads here. And then, all right. So the idea of the hypothesis test is, imagine we did have a fair coin and we flipped it 50 times. What is the probability of observing a number of heads at least as extreme as what we actually saw with our real coin? And rather than explaining that in words right now, let's just go through the code of how this is done, and then I think this Monte Carlo simulation will just give an idea of what's going on here. All right, so here's an example where I've used this a linear congruential generator to generate 50 flips of a coin. Here, haven't done this yet. All right, so here we are. We're going to do a Monte Carlo simulation. So we're going to flip this coin, what do I have here, 100,000 times. We're going to do 50 flips 100,000 times. Question? Yes. Good? Cool. All right. So, loop through here. All right. Close. All right, so I've flipped, as we loop through here 100,000 times, we're going to flip our coin 50 times, our simulated coin here. Let's count the number of heads. Okay. Need to have a place to accumulate these. Okay. Make this a little smaller. All right, but here is, we did our simulations, and here is our null distribution. So this is the distribution of outcomes we'd expect to see if we were to flip a coin 50 times. How many heads are we likely to see? If we repeat this process many, many times, this is the distribution of the number of heads you're likely to see. All right, any questions or? All right, so then we look at our so I've done something silly here. I've overwritten my variable from before, so I'm going to go back, regenerate this. All right, here we calculate the observed number of heads we saw, and then what is the probability of seeing this many heads or fewer? So we have close my brackets. Oh, I missed out of 4. I've done something silly here, so I'm gonna go. Oh wait, I see, I'm treating it as if it's a list, but it's an array. Alright, I got this. Sorry, I'm a little tired at the moment. Alright, so I'm taking the observed number of heads, and then I'm calculating in the left tail, it's so the left tail, I just look at all the instances where simulated statistic is less than or equal to the observed number of heads, get the proportion of those. Similarly, the right tail, I see. All right. Sorry about that. I did this now. All right. So the basic idea here is we just found the probability among all our simulations of observing something under the null distribution here, less than our observed number of heads, and greater than our observed number of heads. And then I want the probability of finding something more extreme than that. And so I'm taking the minimum of these left and right tails, that's going to be the smaller of them, and I'm multiplying by 2. Does anyone know why I'm multiplying by 2? It's the, yeah, I'm comparing, because I want to test if the coin is fair or not, so I want if it's either too big, too many heads, or too few heads, then that's a sign it's unfair. So I'm actually doing 2 comparisons here. So in order to find something at least as extreme, we have to account for the possibility of the number of heads. If we saw 47 heads, wow, that's like astonishing. We'd have to account for the possibility of it being as extreme in the other direction, because under the null, we would have been equally surprised if that had happened. Does that make sense? Any questions? All right, so then I'll make some nice plots, which will, it looks like I'd called these. I'm making some plots just to illustrate that in a moment. All right. So this code here will plot this null distribution, and it will shade the tail. All right, so the number of heads I found here. Right. Right, sorry. All right, so I had found 24 heads when I did this, so looks like I have an off by 1 in this, but yes. Yes. Yeah. Yeah. Yes. Something's gone wrong with this where it's shaded the shading has gone wrong. This one should be blue. Yeah, the intent was to shade. Yeah, at least as extreme. Yeah. So that's the tail probability. It's the probability of something at least as extreme here. And then if I go back and I make this less fair, all right, so I've added more heads. Now my p-value is 0.202, which means that the probability of and my observed number of heads was 30. So the probability of observing at least this extreme of amount becomes 0.202, and why is this? I think I have a wrong variable name somewhere, and that's why it's doing this. Yeah. Oh, here's my wrong variable name. I got this variable name fixed. This should have been observed numheads here. I wrote numheads. All right, but here is the example now. This tail, the probability of having in this distribution at least 30 or more ends up here. And then we have to account for that it could have been as extreme on the other side. We have to double that. All right, but then, see, I fumbled my way through that because I'm a little sleep deprived. All right, try to pick up steam here, but then it's much easier to do this with SciPy. So you can use, first of all, you can use SciPy.stats to generate sequences of 50 coin tosses from the binomial distribution here. So this is a binomial distribution. This first one here is your n. So this would imagine is the number of flips. We're just flipping once here. This is a p. This is the probability of getting heads, and we're flipping 50 times. So we flip a coin once with probably a fair coin. 50 times we get that. And then we look at how stats Monte Carlo test works. And this is pretty nice here. So it takes, first of all, a sample. In our case, this would be your sequence of tosses that you had generated yourself with your imaginary coins. And then the second argument here is a function that calculates a statistic. In our case, this would be the number of heads. And then, sorry, that's the third one, is the statistic. The second one is the process that generates the data. So, whereas before, even though I should know this stuff very well, I stumbled through it. It becomes very easy to do this test in SciPy. So, stats Monte Carlo test, we have our number of tosses. Had put this on another line. All right. All right, so we see, all right, so this sampling thing must accept a size argument. So it's going to generate a sequence of a given size, and it's just going to match that up with the size of your sample later. And then here our statistic is simply NP sum, because we're just going to add up the number of heads. So yeah, it's going to call that on each sample, and it's going to do this calculation from before. Can plot my null distribution. Again, it has a attribute. The null distribution will also have a p-value and the statistic here. So I can use that again. And if we look, the p-value is roughly the same. The reason that it's a little bit different from before is because this is a simulation. As you can tell, I don't spend a lot of time writing this stuff in regular Python. I thought I'd be more fluent there, but yeah, it's really easy in SciPy. All right. All right, before we move on to the activity, does anyone have any questions? I promise this is going to get more fun. Yes. Is it a little up? That was your coin tosses you generated at the beginning. It's an imaginary coin. Yeah, so it gets generated, it gets turned into an array in this cell. All right, raise your hand if your coin is fair. Who got a p-value? Well, I guess who got a p-value like? I guess whose coin is unfair? Who got a p-value less than 0.05? What was your p-value? But were most people able to generate unbiased sequence, or at least as far as this test is concerned? All right. Is everyone ready to move on to the next part of the activity? Do you think they should have a little more time? Sounds good. All right. Yeah. All right. So you tested if your coins are unbiased, but does that test if your coin is random? Not really. It could be, I mean, you could just do 1, 1, 1, 1, 1, 1, 1, 25 times and then 0, 0, 0, 0, 0. All right. But, all right, so the idea of this Monte Carlo test, though, is that you don't really have to fiddle with analytical calculations of the distributions of things. So you just need to think up a statistic that would be sensitive to randomness. And then if you have something like that, then you could just plug it into this test. And if your value is extreme under the null distribution of the statistic, then you're not very random. So I think the idea here is collectively we're going to try to brainstorm the statistic, or some statistics which will be sensitive to the randomness of a sequence. So what is an idea? All right, the randomness of a sequence. We don't want to be able to predict the next sequence at at odds better than chance. We don't want to be able to predict the next entries. Now, does everyone know the gambler's fallacy? This is like a gambler might see the coin come up heads 6 times in a row and think, okay, tails is due. Or like it came up, heads 6 times in a row and then, oh no, tails is really strong. So the thought is, these flips are sticky. If it's more likely to if it's come up heads in a row, maybe it's more likely to come up heads again. Or maybe it's less likely. So based on this, does anyone have an idea of a statistic which might be able to show, be sensitive to randomness? Yes. All right, so yes, did everyone hear what he said? No, it's how often the result changes. So count the number of times that you have a run of 0, say, and then it changes to a 1, right? Because if this coin is sticky, and the gambler's right that if it comes up heads a bunch of times in a row, it's going to come up heads again, it's going to change less than a random coin, right? And if the coin is the opposite of sticky, if tails is due because it came up heads a bunch of times in a row, then it's going to be, more changes than expected. It's good. So the idea here is implement this statistic, or if you want to be creative, think of your own statistics. You could try multiple things because we have some time, and use this Monte Carlo test to see if your sequence is random. And then since this is activity, I can go around too and see how everyone's doing with this. And we have, time is it's like 2:15. We have like maybe 20 minutes to work on this. Yeah. Who has a p-value? Show of hands. Who was able to generate a random sequence with a significance level of 0.05? Whose sequence was not random? Anyone? Yeah. Mm-hmm.
We got a 0.006 here, so that was pretty unusual for the.
Yeah. I have if anyone's, I have like an example solution up here now if everyone wants to see this. Or does anyone have any questions about this? Does everyone have a p-value? Does anyone need more time? All right, how many people got below 0.05? 1, 2. Does anyone not have a p-value? I guess. All right, so I think you guys are pretty good at generating random numbers then. All right, so this was a study, this was like a real study that was done about, and it's one of those psychology studies that doesn't replicate, or at least the results come out different every time someone tries it. But when they did this with psychology undergraduates, they could not generate random numbers, at least on the whole. I saw another study where like they gave like a couple minutes of coaching and like then people were able to. This is not a perfect test for this. When they include this test, like to benchmark random number generators, they do like millions of samples, not just 50. But I hope you appreciate that I didn't have you all do that. Okay, I think we can have like a 10-minute break or so. If anyone has questions, feel free to ask. Matt, is that you think that's enough break time, or you think? All right, I guess for a minute I can just like step through my solution. I think everyone got this. So I want the number of times this changes. So I take a logical XOR between first one, line up the first, all but the last one, and then shift it off by 1, and then all but the first one, and then XOR is 1 if they're different, or 0 if they're the same. So this sum here will count the number of changes. Yeah, and then I just set up the Monte Carlo test with my random sample and the statistic function. I use binomial. Yeah, I change it. The binomial distribution with n equals 1 is equivalent to the Bernoulli distribution. So I just I forgot that SciPy had the Bernoulli distribution. Yeah. Yeah, right here I'm running it. And then this wait, that's binomial, right? Is it binomial in NumPy, or is it? Yeah, I always get those confused. All right, yeah, but they do. These are equivalent generators. All right, so then the next section is going to be on permutation tests. All right, I think I had in case, I just let everyone click through here. I had in case people were in here didn't have much statistics background, I reviewed hypothesis tests. I think people, for the most part, get it. I just go through the null hypothesis is our default, our boring understanding of what's going on, and then any apparently interesting phenomena is just to be explained as random variation. In our case, that was the probability that just fair coin, independent tosses of a coin that comes up heads half the time. Alternative hypothesis, loosely speaking, is just something more interesting that we want to try to investigate. Maybe it's true. Then just go through all the... all right, and then we had our test statistics. Should be sensitive to the question of interest. So the number of heads was sensitive to whether or not the coin is fair. This count of the number of changes is sensitive to, the stickiness of tossing, which is a measure of randomness. A random coin should not be sticky. We had that null distribution, just the distribution of your test statistic, assuming this null hypothesis. And we had these different tail probabilities. Probability at least as small as the observed value when the data is being generated according to the null, or at least as great. And I said the p-value was at least as extreme, which I was including both tails because I want to include both of these comparisons, and that's why I had to multiply by 2. So then some other ones, probably where there's the idea of the significance level. It's like your p equals 0.05 cutoff you see in biomedical studies that people try to p-hack their way towards sometimes by trying a bunch of different things and only reporting the stuff that worked. I think that's the main reason why these frequentist hypothesis tests are often not recommended now as a warning against p-hacking. But if people use these things diligently, it's a useful tool. It's what it's doing is it's controlling the type 1 error rate, which is the probability of rejecting the null hypothesis when the null is true. All right, so for this notebook, brought back this function to plot the null distribution because that's going to be useful. And then just as another example, there's a tail probability. All right, I made this, I had the size set up for when this was not control plussed quite so much. So make this, everyone make that a little smaller, I guess, in your thing. Or maybe not, because you're on, you don't have to blow it up. That's how you would fiddle with the, where was it, the size of this plot, just fig size. All right. All right, so some other things here, just the two-sided test we went through, but there's also the idea of a one-sided test. Like what if you wanted to test if someone had a coin that was biased towards heads, they're trying to cheat at a coin tossing game. They're going to get, they get the ball first in football or something with their biased coin. All right, so we don't care if the coin is biased towards tails in that case. We want to check if it's biased towards heads, so we only have to look at that one tail for heads because we're not making two comparisons there. All right, so then the experiment we're going to look at was conducted by Charles Darwin, and it's examining whether cross-fertilization has an impact on the plant's growth. So plant is cross-fertilized if the pollen from one plant is used to pollinate another plant, self-fertilized if the plant, pollinates itself. And then I guess the idea is like a kind of a hybrid vigor kind of thing, like the plant, is the plant that is cross-fertilized going to grow taller? And I think Darwin was a pioneer at understanding these kinds of things at this time. Looking at this, so he set up pairs of plants and tried to keep, for each pair, he tried to make the conditions exactly the same, except that one was cross-pollinated and one was self-pollinated, so in the same pot, in the same conditions, in order to make this, eliminate this source of variation. All sources of variation except that the fertilization method is different. So in this cell here we have our data set. All right, and the null hypothesis here is that the method of fertilization has no effect on plant growth. And the alternative hypothesis is cross-fertilized plants will be taller. So is this a one-sided or a two-sided test? One-sided, yep. All right, so then we have to choose a test statistic here. First of all, since we're matching these up, it's good to work in terms of this difference. This D here is just the how much larger or smaller, if it's negative, the cross-fertilized plant is from compared to the self-fertilized plant. And decent statistic here I guess I don't actually need to implement it that way. I'll just take the sum. If the cross-fertilized plants grow taller, then we should expect the sum of all these height differences to be positive, because you have, each plant should be bigger. If we actually look at, I'm not good at Colab versus a regular notebook, but if we actually look at the value of D, we see sometimes it's negative, sometimes it's positive. It's kind of more often positive than negative. But since it's positive, it makes it seem like, it's probably some kind of effect that the cross-fertilized plants grow taller here. And all right, so how do we simulate the null distribution? So remember before we were doing a Monte Carlo test, but before that relied on us knowing an underlying distribution for our process. We were flipping a fair coin, and then whatever statistic we had, we need, it's just derived based on that. It's just some function of these tosses, but we don't know anything about the distribution of these plants, right? Someone can make a normal assumption, but without testing that might not be justified. And Fisher went through this analysis because he wasn't sure if this was justified. But, all right, if the method of fertilization makes no difference, then whether or not a plant was self-fertilized or cross-fertilized shouldn't even matter. So whatever group each of these examples is in, whether it's in X or it's in Y, shouldn't matter. Like, there's no statistical difference between, I guess there's no difference based on cross-fertilization or self-fertilization why these would be different. Any difference would just be random variation. So in that case, in order to generate a null distribution, you can look at all of these and just randomly flip them. Like you look at each one, maybe I go this way, flip this one, not this one, and so this is called a permutation test. So this is how Fisher describes it. I don't think you can read through that if you like. And all right. All right, so we go through the code here. All right, my statistic is the sum. And if we're flipping those, then all that amounts to is we're changing the sign of each entry of this D if we switch it from one group to the next. So it's like, all right, if the cross-fertilization plant was taller in one case, in a resample it might be smaller in chance by another. So, and we don't have to sample these randomly because this is small. We can look at Y, like we can look at all possible. All right, so I have iter tools. So I can look at so this thing I've done here is, wait, this should be, okay, this thing I've done here is I take the, I take a sequence, a list of tuples, 0, 1, of length D. I am using unpacking here to feed this into the argument of a Cartesian product. So I think this should be -1. So this is giving all possible ways of, make sure I have this right because I get, just look at this actually. Just copy it down. All right. I'm just copying this from somewhere else so I don't mess it up again because I'm quite sleep deprived. Not be a good day to push something to production in a state like this. All right. Yeah, I need n is length of D. Signs is this. We're looping through all the possible signs. And then we're computing our statistic and we're multiplying. We're using broadcasting here to multiply our input sample, each one in turn by the different signs, goes through all the different ones, and that makes a null distribution here. And all right, so then I set D equal to this, and all right, here it is. This all right, it needs to be smaller. All right, you can't see the top, but there it is. So this tail here that gets cut off looks pretty small, right? So this, according to the null distribution from these permutations, it looks like this is probably significant. We can look at the p-value. I calculate that up here. All right. Yeah, so it ends up in just 863 out of the cases, the total deviation will be greater than what was observed, the statistic. And look here. So our p-value is 0.02633, and this is a estimated p-value actually, but in this case for a single comparison it works pretty well. So this is significant using our 0.05 criteria. So then let's do this the SciPy way. So we have, like we had the Monte Carlo test, we also have the permutation test. It works in the same way for the most part. First entry is our data. In here, permutations tests can work with multiple samples. Some of you might know like there's like a one sample, like this paired test, or you could have like a two sample test to compare the difference of means, like a two sample t-test. This example has one sample, so we have to put this in a tuple of length 1 with this sample. Our statistic is just the sum. All right, our alternative hypothesis here is greater because we only care about the right tail. It's a one-sided test. All right, and then here's the interesting part. Permutation type equals samples. Now this name might not be clear immediately what this means, but the idea is that this will flip. If you have this, will flip the signs. In this case, it does the same with permutation type equals samples. All right. Other things don't. All right. And all right. I threw an assert in, and the p-value came out exactly the same. Close this out. So that's yeah, it's much easier than trying to remember how to do that from scratch on the fly. Oh, which one? Say. Oh, of course. Yes. Yeah, you can. Okay. Yeah. Okay, before we go to the activity, does anyone have any questions, comments, anything? Or just want to flip back through other parts of this, maybe? Okay. It's inside of a list. So this ends up being, signs is this thing, it's a tuple, and you get a list of them of length n. And then this, you unpack it so that it becomes the argument, they each becomes the arguments of this Cartesian product. Oh, okay, yeah. So, yeah, so this thing here, yeah, so imagine, so before we unpack, it looks like this. It's a list of these things, and then when you take the unpacking with this star operator here, you end up, these become the arguments of product here. 15. So then it takes the, this will iterate through the Cartesian product, so it'll go through like every single possibility of length 15, say, of these things. And then for the activity, it's going to be the same basic setup, but a practical, like a modern example. Keep this up a little more. Everyone ready for me to explain the example? Alright, so this is based on an actual project my wife and I worked on when we were doing our PhDs in the same department, and also partly based on like some work that was going on in the lab I was in after I graduated. Alright, so Alice and Bob are working to train classification models to predict whether breast cancer patients will achieve pathological complete response. So what this means is, in response to neoadjuvant chemotherapy. What this means is that prior to surgery for breast cancer, patients are sometimes given a round of chemotherapy to shrink the tumor to make it potentially easier to conduct the surgery. There'd be less tissue to remove. And we were working on trying to, and then pathological complete response is a technical term for where there is no sign of tumor tissue after a biopsy. And this is done based on gene expression profiles. So I don't think, like, if you're interested, I don't think you have to know the biology to appreciate this example, but like all of our cells, every single cell, no matter how different it is, has the same DNA in it. Genes are always being converted into proteins, which are the machinery of the cells, and different types of cells have different genes switched on and off, different expression levels. And we looked at the gene expression levels within the tumor prior to neoadjuvant chemotherapy, and we tried to predict whether pathological complete response took place. And there are two models here under consideration. One of them is a humble random forest model, which has served as the baseline model. This is a classical machine learning model, like developed in the 1980s based on decision trees. This is what my wife and I used in our, like, the project we worked on, the other classical models. And the other thing is a sophisticated graph neural network, which takes into account the graph structure of known protein-protein interactions for all these genes. Just a very sophisticated, fancy model. In the lab I was at after I graduated, was doing stuff with graph neural networks of biological protein-protein networks. there may or may not be bugs in this thing because it's so complicated. And the model is attempting for each patient in a data set, it tries to predict the probability of pathological complete response. And the models are being evaluated using the area under the receiver operating characteristic curve, which basically gives the probability that if you have 2 points you're evaluating on where one of them has the probability of PCR is greater than the other, the probability that they're not discordant, meaning that the higher probability one doesn't have PCR and the lower probability one does. It's not important for the example here, but just, and then we're using 10-fold cross-validation. So there's a data set here of 147 patients. We're splitting this into 10 equal groups, and for each of these groups, we're holding out that group and training the model on all 9 of the other ones, and making predictions on the remaining part. Some of you might know that like you need to have more splits in this. So we just, if there's model selection going on, it's going on in the train fold. So that you end up with 10 evaluation metrics where the training data overlaps a little bit, but the validation data that you're making predictions on and calculating this metric are different. So you get 10 values of this metric. And better, I went it backwards. Better, higher is better for this metric. And why is it, first of all, why is it important to use the same exact splits when evaluating both models so that we train on the same split and evaluate on the same split? Just try to catch you awake. It's the same reason why Darwin put the plants in the same pots and gave them the same, try to get the conditions the same. It reduces the source of variability. I just made up some plausible sounding numbers. I couldn't find the data for the random forest experiments I ran, but they looked around like this, and I just made up these GNN results. It's just to illustrate a report. So the cell has this here, and so a journal article might report the results in a table like this, and this GNN number, it's bigger. It would probably be in bold in this to show that it beats the benchmark. It is the best one here. We've reported some standard deviations. So I think in a lot of machine learning papers, this might be counted as like a successful positive result. Like we've beat this benchmark. Let's not worry about how many different things we tried. All right. But based on this data, can we be confident that this graph neural network is actually performing better than the random forest, or could this just be random chance? And then this is a very noisy problem. So there actually is a lot of random chance in how these things do. There's just not enough information in these expression profiles to really predict if PCR is going to happen. There's all kinds of other factors. If this was like some like image classification problem, it probably wouldn't be so noisy, and like this probably would be a significant difference. But all right, the task here is to perform a permutation test to investigate this and to plot the null distribution using that plot null distribution function from above. And then I'll put the other example up here of how this works so you can look at it, and then please let me know if anyone has any questions or anything. Okay, let's get back to it. So I think you've noticed that this example was set up exactly the same as Darwin's experiment. And I did that on purpose because I wanted to show that this same exact test would be applicable for a modern situation too. You also may notice this null distribution doesn't look normal at all. So gives an inkling that a test that had assumed normality might not have worked so well, and we're going to show that in the next one, if we can have time for that. All right, so yeah, now we're going to the bootstrap. And I feel like, when I first learned about the bootstrap, I thought it was like magical. Like, it's like, how does this even work? It's where you make inferences about some statistic, like you try to estimate, like you're estimating like the number of heads or how well a machine learning model did or something. And you want to you want to estimate your uncertainty in this estimate. You don't want to just have a point. Maybe you're really certain of that, maybe you're uncertain. And the bootstrap can help with this. The creators, I think, thought it was magical too, and that's why they called it the bootstrap, is you literally pull yourself up by your bootstraps. So let's look at this cross-fertilization data set again. And all right, so we did a permutation test on this data set to study whether or not the method of fertilization had an impact on the plant height. But a lot of times we're not just interested in whether or not there was an impact, but the size of the impact. But it might be, it's not ideal just to report this difference that we see in plant heights, maybe a mean difference in plant height, because there's uncertainty in that. And we kind of need to know the possible variation there. So we want a way to incorporate the uncertainty. So like here's this difference here. What does that even tell us? It could be if it's up to chance or something. All right, so here that's a point estimate. I mentioned it's just 1 point. But then some of you have seen this idea of the confidence interval, which is, I think, often misunderstood. So you have some significance level, like say you're making a 95% confidence, and then the confidence interval, there's an algorithm that you have based on the results of your experiment, like based on a sample. The algorithm generates an interval which covers points. So if the, if you're looking at ROC AUC scores between 0 and 1, like you get an interval, say from like 0.72 to 0.76 or something. That would be a pretty tight model compared to what we had before maybe, but that's your confidence interval. And what goes on is if you ran this experiment again and again and again in a frequentist way, and you apply this algorithm each time, you want to design this algorithm such that if it's a 95% confidence interval, then 95% of the time, like the true effect size will be inside of this interval. What do I mean, like true effect size? Well, it's like, in the frequentist sense, it's like what is the actual expected value of this thing over the long run. That's your... All right. So now if we knew the distribution of the effect size, which might be like a, that's like a statistic we have maybe, then we could just generate the confidence interval just by chopping off the tails of this thing. We could cut off 2.5% from the left and from the right on one of those pictures, and the probability of what's in between is 95%, and that gives your interval. But we don't know this distribution necessarily. Sometimes you can assume what the distribution is. You might assume it's a normal distribution, and then estimate the parameters of that. But a lot of times the assumptions, these assumptions don't even come close to holding, which I think was true in that machine learning example, and we'll see here. So what if we use the permutation distribution? Like, does anyone think that might work? The permutation distribution, would that give a distribution of the effect size? Well, I think the answer is obviously no, because otherwise we would just talk about that and we wouldn't have a new title for this thing. But yeah, the permutation distribution gives a null distribution. It's the distribution of your effect size under the assumption of the null hypothesis. That might not be true, so we need some way to estimate this actual distribution of the effect size. So how do we do it? We pull ourselves up by our bootstraps. All right, and then walk through this again. All right, so here we're just going to instantiate a random number generator. And then, let's see, I'm going to make 10,000 samples here. And then let's make some just from goes 0 hold on. Matt, what is, I know I can just look at the, I need to look at the documentation of this thing. Oh no, it's rng.integers. Integer. No, I think I just, oh no, I didn't, yeah, I never ran that code. That's the problem of putting this all in the same cell, is that I don't want to run it because it's going to error out. All right. I have this, and integers. All right, I want low to high. All right, that's what I thought it was. So indices can go integers 0. All right, is it inclusive or exclusive? Exclusive? Oh, depends on the endpoint argument. Endpoint is false. Alright, it's exclusive, so the size equals, alright. Alright. So yeah, I've used this to generate random integers between 0 and 14, which are possible indices into this thing before. And I've made it the same exact size, 15. So what this is doing is letting me sample from this with, all right. Let's see. And then the important part here is that we are resampling with replacement. So each index that comes up in this thing can appear again. We don't throw out a data point because we because we already included it. All right. So then I have a resample, and then bootstrap distribution, append sum. Okay. All right, yeah. So this, it looks like I'm missing a little bracket. Oh, I put this on its own little thing because that box was still there. Okay. This doesn't seem. that right? Yeah, it is right. Oh. No, it's plot dot figure. Just want to make it a little smaller. There we go. All right, so this is a bootstrap distribution. Now, who here just like this intuitively makes sense that this is gonna estimate the actual distribution of your effect, this difference? Literally no one, right? Like, yeah, this is just this. I still like. It's like I can work through the math, but like it just seems absolutely wild. But then we can make a confidence interval from this thing by just cutting off the percentile values. And here we have a confidence interval, which is pretty wide. But you notice that every single value is above 0. Do you think this has a relation to the hypothesis test we ran before? Yeah, there's actually there's kind of an equivalence with hypothesis tests and confidence intervals, that if your 95% confidence interval for some point has every single, yes? Yeah, let's look at the mean. Yeah, those are the sum. Yeah, I had done the sum before. We could change, yeah, it doesn't. Yeah, I think mean is better here. If we're just getting a p-value, then it doesn't matter, but if we're getting a confidence interval, yes, we want the mean. It's a good point. All right, and now, all right, here's our potential effect sizes, how much bigger on average a cross-fertilized plant would be. And so presumably if we were to run this experiment again and again and use this method to calculate the confidence interval, then this true unknown value of how much impact cross-fertilization has should be in this interval. And, okay, but like how? All right, so I think you all know, like this, I've probably seen the idea that you can take a sample and you get a sample mean. Or you can take a sample, so you've seen you get a sample standard deviation. And these sample things are, if you know, like the people who've had more statistics background, this is called the maximum likelihood estimator for these quantities, for a mean, which is the most likely value of the mean given the data. It's like you take a probability distribution that depends on a mean and you turn it around backwards so that it's a function of the data instead of a function of the parameters. And then whatever the most likely value is there is your maximum likelihood estimate. But you can estimate things that are not just individual points. You can estimate a probability distribution. So what this bootstrap thing is it's the empirical probability distribution calculated from a sample. It's like the sample probability distribution. And it's actually, if you want to like check out the math, anyone's interested, it is the maximum likelihood estimator of the actual probability distribution. And so that's why it works, but it like, I'm still searching. I want to feel it in my bones why the bootstrap works, but it's still, yeah. Yeah, but it's very cool. So now we can do this with SciPy instead. So here is the signature for that. It works similar to before. We have a data, and we have a statistic. Notice we don't need to like we don't have like the Monte Carlo test, we don't have to sample the data. We have that here. We don't have to give, I guess there's a lot of stuff here that you're going to have to like look into later, but we're just going to get to the, all right. Data is x minus y. And result data, the statistic function is just yes, good catch. Yeah, we need to put this in a tuple again because this can work with multiple samples too. All right. So, okay. I have this here. I want to make that same plot again. And I want to make the same confidence interval again. Oh my god. Oh, but that's not the right thing. I want... So here I put the previous one, but I want result dot bootstrap distribution. Okay. And it's no different than the previous one because it's a randomized method. It's not going to come out to the same every time. We're only approximating this distribution. If we oh, yes. Oh, it's also BCA, yeah. I need to, thank you. All right, so I did this in the, oh no, I did this by hand, manually, instead of, I see. So that is this, yeah. But yeah, we can get that out of the this result. I should make it, all right. So in order to make this actually equivalent, I need to set method equals because you think given a distribution, there's a lot of different ways to chop off part of it to leave 95% of the mass somewhere. So there's always going to be multiple methods. Method equals percentile does this equal tailed thing, which I think is good for show here because it's intuitive. Yeah. So, yes. So dot bootstrap distribution could catch. All right. And then, yeah, if you run this many times, it's going to come out a little different each time for your confidence interval. But if you increase your number of resamples, it'll start to stabilize. I would, I think it depends on the problem itself. I'd probably do a simulation or something to see. Yeah. Yeah, I think you would do something kind of similar here where you could like do like a increase your sample size exponentially to see where it starts to level off, and then kind of like backtrack to like do a yeah.
How many do you have time to remember?
All right. It's all right. So what's going on now is it seems to have like two different intervals that it's that's interesting. It's like converged to. I did BCA again. No, I didn't. Huh. All right. I'll look into why that's going on later. But all right, that's the SciPy way. All right. So then. All right. The activity is here. I guess before we go on the activity, does anyone need to see more of the code? Yeah. Do you want, which one do you want? Yeah. Yeah, just the, yeah. Oh.
I thought bootstrap was like, I have two observations. Bootstrap.
No, you need a lot. Yeah.
But here we have, we're doing 50. Like, this is our total.
Oh no. All right. This is I see. All right. That's a good question. Okay, yeah. What I like to do is like generate synthetic data sets from like some, like use like SciPy's like random sampling for like different distributions, and generate synthetic data sets of different sizes with different parameters, and just like simulate how the different methods work to just get a feel for them. It's probably like I'm not even sure. Matt, is there like a theory on this, or is it just from like experiment that people have a sense of this? Like I don't. Yeah, the only way I've looked into it is like experimental. Yeah. 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 Oh, yes.
So, for an arbitrarily high number of samples, should the distribution be exactly centered on the mean of your data set, or is
Yeah.
for something that you're going to be a bit of an odd?
I think it should be Yeah, because it's the MLE for it's an unbiased estimator for and I think it's also it's a consistent estimator. So right, I think so. It's like as the sample size increases, it does converge to the true distribution.
So I've run like a number, like I just keep increasing the number of samples, and I got to like a million, and it's still like, 51 point something percent of values are on the
Yeah.
right of the median. So it's a little bit.
Well,
We are doing the mean thing, right? Which is, so you would not expect it to be biased.
yeah, you don't know. Yeah, where do you know the mean from?
The mean of the sample.
No, that doesn't need to. No, it doesn't need to have. It doesn't need to. The me- yeah, no, it doesn't have to. Yeah, it doesn't have to become centered on the statistic for the original thing. That's like, I think that comes down to like Jensen's. Well, that's a mean doesn't matter for Jensen, but it's like it's like, yeah, it doesn't have to become. Maybe it is. It's like you calculate this bootstrap distribution. Yeah, it does not have to become centered on your original statistic value, because it's like it's a very non-linear thing to map like a sample to a curve. It does. Oh yeah, have you looked at the mean? All right, have we looked at the mean of the? Are you looking at the plot, or are we looking at the mean of the bootstrap distribution?
So I'm calculating so basically what I did was, I'm basically taking my bootstrap distribution and I'm seeing the proportion of values that are higher than the mean of the sample difference. And it seems like it's like, to me it looks like it's converging around.
Okay. Here's the this here's the mean. Yeah, I took the mean. This is the mean of the bootstrap distribution here, and then yeah. What was it called? Yeah. Oh, it's yeah. I was talking nonsense. Yeah, it does. It of course it converges to the same thing, and yeah. Oh, you know what? Yeah. Yeah, it's not just good. You can't just increase the number of bootstrap replicates. You have to increase the sample size of our 15. That's what makes it. Sorry, that's what makes it converge. It's going to converge as you increase that number of samples. Like that's where the asymptotics are. That's right. And then, so it doesn't. Yeah. Yeah, I think it's good. My intuition is it's gonna plateau at some point or something unless you actually increase the actual sample size. Yeah, I guess it's going to converge. It's going to converge to whatever the actual. No, yeah, it's like could be. Okay, and then, so then we're going to try this out for an activity. So in Efron and Tibshirani's book, Introducing the Bootstrap, they talk about this. So it's a new medical treatment to prolong life after a form of surgery. 16 mice are randomly assigned to either a treatment or control group. It's under the constraint that only 7 treatments are available. All mice receive the surgery, only the treatment receives the treatment, only the treatment group receives the actual treatment. And here's the data. And then, okay, we have an actual statistic here. And then the first step is a review to go back and perform a permutation test with stats.permutation test. And the second step is to do the bootstrap. But I think we can do, in the interest of time, we can do this permutation test together and then get onto the bootstrap. So I'm taking, and I'm going to want to look at this documentation again because I do not have this memorized. Okay. So now our data here has 2 samples instead of 1, unlike before. So we have a tuple with these 2 in it, our X and our Y. And then our statistic is just statistic. Permutation type is now independent. So we're not, instead of shuffling each one from one sample to the next, you just shuffle them completely randomly between the 2 groups. And then we need the alternative. We need to go the alternative is greater. We're interested if the treatment increases. Result of this. Okay, and then here we have our statistic. We have a p-value which is not significant according to this, although our statistic value here, this difference in means, did seem like it was pretty large, but that's why we have to run a hypothesis test. All right. So then, but what if we're actually interested in estimating this effect size? So the goal here is to use stats.bootstrap to estimate, like I guess to estimate a confidence interval in this case. And to plot the distribution again. Yeah, it's activity. Before we go, does anyone want to see the last example where we go back to that machine learning thing and like show that it's not normal? All right, let's, all right, this was an activity. This was an activity if we're really, really ambitious, but it's just going to become coding. All right. Statistic, mean method. All right, so I'm generating this. Wait, oh, I didn't even run that cell. All right, now I'm going to run the cell. Oh wait, what did I do? Oh yes, yes, it needs to be a tuple. I always mess that up. No, remember I reviewed the PR and like I signed off on this. Remember?
It had to be that way.
Yeah, I was yeah. Wait, what am I doing now? I forgot a comma. No, I forgot a comma. Another comma. I struggle so much editing these things in Jupyter to like. All right. So I want to see the result here. All right. So as we see, the confidence interval contains 0. All right, and then I had this function. I should just copy from somewhere else. All right, so it's looking a little skewed here. And then, all right, so we're going to use the normal test, SciPy. Tests, the null hypothesis here is that a sample comes from a normal distribution. So the alternative is that it does not. So a very low p-value means not normal. Yeah, all right. All right, it combines the skew and the kurtosis. And all I need to do is pass in the sample here. Bootstrap distribution. All right, and our p-value is 2.45 something e to the negative 18. So it's very, very small. So this is not. And then if we were to actually like do. All right, so then if we were actually going to do like a t-test. T-test. Independent of. No, I want a paired t-test. T-test. Rel, yes. All right, and then. And, all right. Oh, okay. Is that a tuple? Two separate samples, okay. And then I want, okay. Oh, right. Alternative should be, yeah, hold on. I need to get rid of this over here because I don't have any room. Yeah. All right, I'm doing recurrent neural network and, all right, RF results. Alternative is greater. All right, so I got a p-value of 32%. Yeah, same conclusion. Actually, it's yeah. What was our actual? Yeah. Oh yeah, we didn't test it. Oh yeah, we gotta go back to the other notebook to see. Pretty close, actually.
Albert put it together, so thank you, Albert.
Yeah.